Okay guys, welcome back to the online lecture. So we are still in the COVID pandemic, so we do the online lecture. So this is mth3103 analysis vector. So this is for the first lecture. I will talk on the briefly on the on very introductory parts of vectors, right? What is vectors and how to define vectors, and vectors in plane and as well as in space, and some operation that involve vector, right? So let me begin with some very introductory definition of vector. So what is vector? Yes. So what is vector? So vector is basically we have a so it must have a magnitude and a direction. Yeah. So vector must have a magnitude and direction. For example, you can consider displacement, velocity, force, and etc. Right. So the notation for vector, so normally we denote as with the arrow. It means from point A to point B, or we can also use that as a vector. Yeah, for example, if you have a vector from A to B, we have the direction. This is our point A, this is our point B. So this is A from A to B, and this we can also denote as A. So point A we call it as a tail, and at point B we call it as a head of a vector. So very basic introduction, and next we look at the vector on the plane. Vector on a plane, and basically 2D vector. So as a first definition, the position vector. What is position vector? Position vector, the initial points or tail, yeah, coincide with the origin. On XY plane. So which means we have, if let's say this is our XY plane, all right, then if we choose a vector, there's a vector from a point A to some point O to some point A, for example, all right, so this is a position vector. Others, if you consider that point to a point B, that vector, this is also position vector. So position vector in this case, I put it as OA, OB. That's position vector, because for the position vector, the tail must be at the origin. But if you have another vector here, all right, from let's say a point R to S, so this R, this is not a position vector. Okay. Then we say if the magnitude of U, so let me define first. We define definition. The magnitude of a vector A, or I can write it as vector AB or A, magnitude of vector AB with the component, let's say we denote as x, y, then the magnitude of vector AB we denote as AB, that this we define as x squared plus y squared. So that's the magnitude. Then if the magnitude of two vectors, let's say magnitude of vector u is equal to magnitude of vector v, and u and v has the same have the same direction, then we say u is equivalent to v. Yeah, vector u is equivalent to v. So that denotes as an equivalent. Okay, then another definition. This is very basic definition. Position vector again. Position vector OP, yeah, where P is a point xy, so we denote as, denoted as OP is equal to xy. So please note that if you write like x, y, this is a point. But if I write x, y, yeah, with that triangle bracket there, or sharp bracket there, then we call this is a vector. A point and vector is different. Yeah, points on xy, so this is a point. So this is xy. But for the vector, this is point for xy, so the vector, this is a vector xy. Okay, so that's for points. This is for vector. And if we have a point P, point xy, and Q, so let's say this is x1, y1, Q is x2, y2, then vector PQ as x2 minus x1, y2 minus y1. So if you sketch this on xy plane, so let's say we have this is our P, x1, y1, this is our Q, x2, y2. So the vector PQ is given as this, right? So there's a vector PQ. This is vector OP here. This is OP. This is OQ. So there's a vector PQ. Okay. I have defined the magnitude. Yeah, if A, let's say a vector A, I denote as the component of A1, A2, component of vector A, then the magnitude of vector A, this is given as A1 squared plus A2 squared. And the direction the direction given as tangent theta as A2 over A1, and theta as the direction, tangent, I think my pen is not good, let me change that. Where's my pen? Here, with different color, I hope you don't mind that. A2 over A1. Okay. That is a very simple example. I think I just skip the example, how to find the magnitude, how to find the angle. Now let's look at vector in space. Vector in space. Okay. So definition for the position vector in space, position vector in space, for, let's say, a point we have P, X, Y, Z is given as OP as X, Y, Z. So again, notice the difference. This is a vector with dot brackets, and this is a point with a curved bracket. Then if a point P, X1, Y1, Z1, and a point Q with X2, Y2, Z2, then we can say the displacements or a vector PQ is defined as x2 minus x1, y2 minus y1, z2 minus z1. Okay, and the magnitude of vector A, or in this case, if we consider this a position vector, so a magnitude of vector OP, magnitude, that's given as x2 squared, where is P here, x1, alright, so x1 squared plus y1 squared plus z1 squared. So if you want to find a vector, the magnitude of PQ, where this is your PQ, alright, so this is given as x2 minus x1 squared plus y2 minus 1y squared plus z2 minus z1 squared. Square root everything. And in space, if you consider the vector x, y, z, so you need to consider three-dimension case, x, y, and z. Then how to plot those vector in space? Let's say you have a point. Here is x, y, z. Let's say there's a point. Okay, so let's say this is x1, y1, z1. Say. So where is x1, where is y1, and where is z1? So how to sketch or draw this? You just make a box. That. Okay, and this is for z. So for z, you just take a line that parallel to that line. So more or less there. This is our z-axis. Then there's a point. There's a vector. There's vector. I use that P. So this is vector OP. Alright. Then yeah, to find the magnitude, I think there's a very simple definition. I don't need to give example for that. So another definition, we say another definition. Yeah, if a vector A, I denote that as a vector A with component A1, A2, A3, and a vector B with component B1, B2, B3, right? Then we say A equal to B if and only if each of those components are equal. So AI equal to BI for I 1, 2, 1, 2, 3. Okay, simple example again. I give you example for this. Example, let's say given A as a alpha squared minus 3, 4 and 3, and given B as a 6, 4, 3, find alpha if A equal to B. So if you look at here, each of those component 4 equal to 4, second component of A equal to second component of B, third component of A equal to third component of B, and first component of A must be equal to first component of B. So what we have, alpha squared minus 3 is equal to 6. Then you can easily solve this for alpha. Okay. Question. A question. If vector A, the magnitude of vector A equal to B, magnitude of vector B, if that, then is vector A equal to vector B. So I leave this for you to answer, to find the answer for that. Yeah. If magnitude of two vectors are equal, is vector A equal to vector B? And give a reason for that. Okay? Give a reason for that. Okay. Next we look at the standard basis vector, a basis vector. Okay, standard basis vector. First thing, what is a basis vector? So basis vector, normally we denote it as we denote as vector I, that as 1, 0, 0, J 0, 1, 0, and K as a 0, 0, 1. This is standard basis vector in the space. So if you plot this is x, y, z, then vector I is one unit in the direction of x. So there's a vector I. This is 1. Okay, vector J, one direction. That's vector J. Okay, one unit in the direction of y, and vector J K. Yeah, there's a one unit in the direction of z. So this we call it as a standard basis vector. If you look at the magnitude of each of those, all of them equal to 1. Yeah, magnitude of I equal to magnitude of J equal to magnitude of K, that's equal to 1. Alright. And of course we can write the vector. Yeah, we can write any vector basically. Yeah, any vector A with component A1, A2, A3 in terms of a basis vector. Yeah, we can write ABC as A1I plus A2J plus A3. Okay, they have the same meaning. Okay, then another definition: the direction for a vector A with component A1, A2, A3 is given as so A, vector A with x-axis, let's call that as gamma. This is cos, inverse of cos A1 over magnitude of vector A. Yeah. Then A with y-axis we denote as alpha. So this is inverse cos A2 over magnitude of A, and A with z-axis denote as let's say beta. This is cos, inverse cos A3 over magnitude of A. So we can visualize this in the diagram. Let's say this is our x, y, and z. So let's say we have a vector A. Let's say this is our vector A with components A1, A2, A3. Then the direction of this vector A is determined by this angle, that vector with x-axis. So let's call this angle as gamma, and with y-axis as alpha, and with z-axis with beta. So in order to determine the direction for the vector in space, we need to determine gamma, alpha, and beta. Okay, just give you a simple exercise. Give you a simple exercise. Easy one. Given a vector A as 1, 1, 1, and vector B as 1, minus 1, minus 1. Okay, so first thing is draw a vector A and vector B. Number 2, find direction A and B. Find the direction for vector A and B. Number 3, find the angle. Between vectors A and B. And 4, find the angle between vector A and vector B, vectors A and B, with the plane xy, xz, and yz. All right, I'll give you two more exercise. Try to think of this, yeah. Okay, this second one, if alpha, beta, and gamma are angle, the angle between a non-zero vector A with x, y, z axis, prove that cos squared alpha plus cos squared beta plus cos squared gamma, this is equal to 1. And number 3, prove that the magnitude of A can also be written as a vector A can be written as magnitude of A cos alpha I plus magnitude A cos beta J plus magnitude of A cos gamma K. Okay, so if you understand the direction vector in space, it is not difficult to prove those things. You just need one or two lines basically. All right, so I think for the first video I'll stop here, then we will continue in the second video. Of course, I cannot make a long record because of the limitation of the my telephone memory. All right, so I stop here. Thank you very much. Bye bye.